electromagnetism, and we started with just magnetism. So if we go over some just magnet basics, okay, remember all that a compass is. A compass is just a bar magnet that is allowed to spin freely. Remember the reason that a compass, the north side lines up with the north and the south side points toward the south, is the Earth has its own magnetic field. And if you were to go to where Santa Claus lives in the North Pole, okay, it would actually act as a South Pole and a North Pole like this, which is why your compass lines up north, south, that way. Okay? Is everybody with me there okay? Remember, you need to be able to draw magnetic fields around different objects. So if I was to say, hey, here's a bar magnet and draw the magnetic field around this, remember the magnetic field points in the direction that a north pole would move. So if you put a north pole there, it would go like this, it would go like this, it would go like this. So you would get this looping around. Remember, these are actual loops. So they connect inside going this way. So inside, they would point towards the north, which is why if we draw magnetic domains, and I have a bar magnet, that those domains would actually point that way. Okay, is everybody with me there okay? Magnetic domains. All right. Remember, this is also magnetic domains is why something like a nail, an iron nail, can get magnetized. Because if you have an iron nail, I'm just showing off my amazing art skills. I know that looks just like a nail. That if it is iron, it has domains. If it's aluminum, it doesn't have domains, which is why aluminum objects cannot be magnetized. But if it's unmagnetized, the domains would all be mixed up. And then if you were to take this and stick this on the end of your bar magnet, the reason that the nail becomes magnetized is that when it's in the magnetic field, these domains then line up. In fact, when you take it off the bar magnet, the domains stay lined up a little bit, which is why it retains a little bit of its magnetism. Okay? If you drop a nail or a magnet, the reason it loses its magnetism is you're knocking some of those domains out of alignment. All right. So magnetic fields, domains. Everybody okay with that? All right. And then we talked about, okay, we got started to get into the electromagnetism piece. So the electromagnetism piece is how does electricity and magnetism relate to one another? And the first thing we said is that, moving charge has a magnetic field around it. Okay, moving charge has a magnetic field around it. We started with, hey, moving charge is essentially just current. So remember to find the magnitude of this magnetic field. You use this equation. Okay, where this was a constant. Does everybody have your formula sheet? You can see it on there. It is right there on your formula sheet, just so you guys can make sure you can locate it. Okay. And then I is your current, R is how far away you are. To find the direction, you would want to use the first right-hand rule and make sure that you guys can do that. So, for example, if I said, all right, I have this one versus, let's say I have my current is going that way for each of those. So try those two. Make sure you guys can do it real fast. Make sure you're using your right hand. This is the test where, you know, if you come in school tomorrow and you take the test in person and I see you using your left hand, I will be like, all right, you're using your left hand. Try that again. When you're at home, it's a little harder for me to do. Okay, so make sure you're using your right hand. On this side, though, you would have into the page. On this side, you would have dots. Remember, the actual shape is a circle going around. Is everybody with me there okay? On this one, the magnetic field would be a circle going around, and because my current is going into the page, it would be going around clockwise. So far, so good, everybody. Questions so far? All right, we did, if you remember, with our first right-hand rule, we did slightly more complicated problems where we had something like this. Let me grab another color. I have blue and I have green. All right, so we did slightly more complicated problems where, let's say, I don't know, you have a wire with current going this way, and then you have a wire with current also going this way. Okay, let's say this is 3 amps. Let's say this is 4 amps. And then a couple of different things I could ask you. I could ask you, where is the net magnetic field 0? I could ask you, find the net magnetic field someplace in between. Find the net magnetic field like at a point over here or over there. Does anybody need me to walk through that a little bit more? I can if you want me to.
Yeah, yes.
Okay, let's do that. So if I was asking you to find where is the magnetic field 0, so then you know you have one of 3 options. It's going to be over here, it's going to be in between, or it's going to be over here. So let's draw the magnetic fields at those various places. Remember, I would recommend on your test tomorrow to use colors, okay? So if we were to do this, see the current's going this way, so if we were going over here, my magnetic field from the blue wire would be pointing to the bottom of the page, negative Y direction. The magnetic field from the green wire would also be pointing to the bottom of the page. So hopefully it makes sense. It can never be 0 over there. Does everybody with me there okay? Because the 2 magnetic fields are going to add. On over here, the magnetic field would point towards the top of the page for the blue one, and then also toward the top of the page for the green one. So again, it can never be 0 over there. If I asked you to find the magnetic field there, just make sure you guys would be using this equation twice. You'd have to use that equation twice, and then you would just add them together. Does everybody with me there okay? Okay. So we know it, then it has to be in between. So if I was to draw it in between, the blue one would be pointing up, and the green one would be pointing to the bottom of the page. And if you're trying to find where the net magnetic field is going to be 0, you would just, essentially what you would do is you would write, well, I would have 4 amps for this one, 2 pi r, and then that would equal mu naught 3 over 2 pi, and then this would be a different r. I hope you guys understand that. So it would be like, I'll call this maybe R2 and R1. And then you guys could solve from there. Do you guys understand that?
I have a question.
Sure thing.
Can you tell me how you got the left arrows, like in the far left, like how you got them pointing down?
Sure. Okay, so your thumb would be pointing like this. You with me?
Yeah.
And then your fingers here would be curling to the bottom of the page.
Oh, so it's the first right-hand rule?
Yep.
Okay.
And then it would be the same for the green wire as well.
Why is it not the second right-hand rule?
Because the first right-hand rule is finding the magnetic field around a current-carrying wire. Okay. Second right-hand rule is where you're trying to find force. So when we're trying to find force, you would want to lay your palm flat, because if you're going to push somebody, you're going to push them with your palm.
Okay.
Okay?
Yeah.
Where this one, we're going like this because there's no force involved here.
Okay.
They're good? Okay, is everybody okay with that? Is that enough? Anybody want me to do more with that, or are we okay? Okay, so that was first right-hand rule. That was the initial thing with that. Remember, I had you guys make an electromagnet. So one of the big uses of this was your electromagnet, and you had a current-carrying wire, and you caused the domains in your nail to line up, and you picked up paper clips, and you were totally amazed. Okay, so that was the first part. All right, then from there we said, all right, well, if you have a magnet, around a magnet is a magnetic field, and if you have current, well, around current is a magnetic field. And then we said, well, what happens if these two interact? Well, you get a force. Okay, you get it's either going to be an attractive force or it's going to be a repulsive force. And then this leads us to these two equations. Remember, they're written, actually, this equation here on the formula sheet, it's written like this. So I'll show you how it's written on the formula sheet, and we'll talk about why it's written that way. And then I'll show you how we've been writing it. But on the formula sheet, it's going to be this, where they write it like this, or they I times L, and they say sine theta of B. Okay, so on the formula sheet, here's why they do this. College Board almost always puts absolute values around things. Well, they always put arrows to represent that it's a vector. They put absolute values to tell you this equation will do a lovely job telling you the magnitude, but this equation is going to do a terrible job to tell you the direction. Because remember, what vector is positive, negative direction. So this is going to be more about telling you magnitude. Most of the time, the reason the College Board writes it this way too is that theta is the angle between these two. Okay? Most of the time, when I write it, I'm just going to write F equals BIL sine theta, just because I think it sounds, F equals Bill sounds better. But this is how I typically write it, but this is how you're going to see it on the formula sheet. But, so these would be problems where, do you guys remember I had you take your red wire, so we're going to pretend that was your red wire, and you put it right over top your little disc magnet, and let's say that the disc magnet had the north facing up. So in essence, let's say our current was going this way, and you had a magnetic field that was dots. Does everybody understand if the north is on the top, why you would have a magnetic field coming up out of the page? Is everybody with me there? And then when you guys did this, you had current, magnetic field. Oh yeah, the force. In this case, the force would be this way. So this is where, to find the magnitude, you do this, and then to find the direction, you had to use the second right-hand rule. Is everybody okay with that? We did some basic problems with this, and then we also had our slightly more complicated, more fun problems, where let's say this time I have a current, 2 amps going this way, and then let's say I had, 3 amps going that way. And then I asked you to find the force on this wire. Do you guys remember doing this? Do you want me to go through this, or are we feeling okay with that?
Yeah, can you go through this one?
I would happily go through that. So I want to make sure everybody understands. The blue wire has a magnetic field around it. The green one has a magnetic field around it. So I have 2 magnetic fields, so I'm going to get a force. Is everybody with me? Thought process there? Okay. So if I'm worried about the force on the blue wire, if I was writing it, and again, I would recommend that you guys bring colors tomorrow, I would write it like this. And here's why I would write it like this. The blue one experiences a force because of the magnetic field from the green wire. And if you do it this way, it's going to be really hard to get this question wrong. So you would then do, let's pretend, I don't know, I gave you this distance. I don't know, it's 1 meter away. So your B would be mu naught I over 2 pi r, where I would be 3, r would be 1, and then you could solve for B. Does everybody follow okay? And then this I would be 2, and then I would have to give you the length of the wire, so we'll say the length of the wire is, I don't know, 2 meters. I don't want to use 2s. 0.5 meters long. And then you would plug in the length of your wire there. Is that okay? To find the direction of it, okay, now I'm trying to find the direction of the force on this wire. If I'm trying to find the direction of the force on this wire, well, the magnetic field from the green one is going to be over there, so it's going to have this, and it's going to point in. Is everybody with me there okay? So I would draw green X's on that blue wire. Now, it's true, I want to make sure everybody understands, there's green X's everywhere over here. So any place like where my hand is, there would be green X's. But I only care about the magnetic field there because we're trying to find the force on that wire. Well, then if you do your second right-hand rule, current, magnetic field, the force would be to the left in the negative X direction. All right, and then just remember Newton's third law. So that means the force on this guy has to be to the right. And if you were to set it up where you were to write F equals B I L sine theta, the number you got would have to be exactly the same. Because it's Newton's third, it's not Newton's third, it's not Newton's third sometimes, it's Newton's third law. Everybody good with that? Okay.
Yeah, that makes much more sense. Thank you.
You betcha. This was, remember I had you guys make motors? That was our basic premise behind how your motor worked. Okay, that you had a coil. The coil had a magnetic field. You had a magnet that had a magnetic field. Those two magnetic fields interacted to cause a force that caused it to spin. Well, your motor was a little more complicated because we had to turn the current on and off in order to get it to continuously spin the same way. Okay? Everybody good? Okay. Remember, we said you don't have to have lots of charges moving. You can have just a single charge moving. And a single charge moving will have a magnetic field around it, which led us to this equation, the QVB sine theta. Now again, on your formula sheet, if you look, they write it like this. Okay, it's here. I'll show you how the College Board writes it. They say Q V sine theta B. Okay. And again, same thing. This is going to be a lovely equation to tell you magnitude, not so lovely to find direction. And then remember the theta is between the velocity and the B. The only thing you have to remember with this one, guys, is that, for example, if I have a positive charge moving this way and it enters a magnetic field pointing into the page versus I have a negative charge moving that way and it enters a magnetic field pointing into the page, the only thing you have to remember is that your thumb goes in the direction that a positive charge would go. So this top one would cause it to go like this, and then the bottom one would cause it to go the other way. Does everybody follow that okay? Okay. Remember also, A lot of times if they're talking about electrons, well, if they're talking about electrons using your constants, you know what the charge is, okay? You know, if there's something where it's like, hey, do you remember there was one question I had you guys do where it was like, you know, a singly ionized thing? Well, that means that just one electron got transferred. You know, if it's doubly ionized, then 2 electrons get transferred. And then also remember, and we're going to talk about this more when we do the mass spec, but also remember it is moving in a circle. So if it's moving in a circle, then you could say the magnetic force equals the centripetal force. So you would end up with QVB equals mv squared over r. And then you could solve for stuff. Like these v's would go away. But remember, if you note, you could find the r and that stuff. Is that okay there? Okay. We did mass spec was next. So let's talk about a mass spectrometer. Remember, a mass spectrometer is, you know, if you watch the CSI or CSI, you know, show, and they have some unknown material, and then they put it in some magic thing that figures out what the material is. Well, that magic thing is a mass spectrometer. Okay, so not always, but a lot of time, mass spectrometers kind of has 3 parts to it. So remember, the first part is going to be where you have 2 plates. The plates are going to be oppositely charged. And the point of this, so if I have a positive charge, it would move this way. The point of this part is, it's called the accelerator. It's just to get the charge moving. Okay, so just remember that in this case, it's going to be the electric energy is going to get converted to kinetic, which is going to be Q delta voltage, not delta speed, equals 1/2 mv squared. Okay. Then typically your second part, you have 2 oppositely charged plates again. And then this part's called the velocity selector. The idea in this part is, well, if I'm looking for a specific object with a specific mass, well, it should be going a certain speed. Well, if it's going too fast or too slow, it's either going to hit the top plate or hit the bottom plate. Only the special speed is going to make it straight, where this object is just going to keep going straight across. Well, if it's going straight across, if you draw your FBD, if this is a positive object, it doesn't have to be a positive object, but in this case, if it is, I would have this electric force going down. So therefore, if it's going to go straight across, I would have to have a magnetic force going up. Well, that would mean if my charge is moving to the right and my palm has to point in the positive y direction, you can see your fingers would have to there would have to be a magnetic field in this part that's pointing into the page in order for that to happen. And then if you set these 2 equal to each other, you would get QVB equals Q times E, where E is the electric field. Remember, parallel plates. To find the electric field, it's change in voltage over R. Again, on your formula sheet, right here. One of the things I hope you guys are getting good at is being able to find stuff on your formula sheet, because like that's an important skill to have. And then your Q goes away, and you could say V equals B over E. So it's kind of one of these things. Hey, look, if I'm moving too fast, that would mean my force M is going to be too big. So in this case, it would hit the top plate. If it's moving too slow, that would mean Fm, the magnetic force, is too small, so then it would hit the bottom plate. Everybody still okay there? And then the third piece, it comes into, this is called the detector. And then there's some magnetic field here. We'll just keep going with X's. And then in this case, it would loop this way. Does it always loop that way? Of course not. But if you measure that distance, D would be equal to 2 times the radius. And then just like we did before, QVB equals MV squared over R. And you can solve for stuff. Mass spec, is everybody okay? Any part of that you want me to talk about? Okay. As I told you before, guys, every single year, except for last year, because last year was a crazy pandemic year, but every single year, there's always some mass spec on your AP test. There's always questions there. Okay, so then we talked about, flux. Okay. And remember, flux is a relative number of field lines that pass through an area. So, for example, if I have a magnetic field going like this, if your loop is vertical, remember the direction of the area is perpendicular to it. Well, if this is my magnetic field, hey, look, no field lines are going to pass through that loop. That would be the cosine of 90. Cosine of 90 is 0. No field lines pass through. Okay, where if you had, like this, that would be the cosine of 0. So your flux would be a maximum like this. And remember, and this is where I'll explain when we talk about generators, if I spun this, I could reach a point where my area points the other way. That would be maximum flux, but it'd be maximum negative flux. Which is why when we did the stuff, if you guys remember the FET simulation, where that magnet was spinning and the current went one way and then the other way, then one way, then the other way. Okay? Flux. Remember, flux is measured in Webers, which is Tesla times meters squared. And then that led us to Faraday's law, which was this. Okay. So remember, you have to have a change in flux. Okay. That, you guys did that FET simulation, the experiment where you had the coil and a magnet. Well, if you just move the magnet so it's just sitting inside the coil, nothing happens. Okay. And it also should make sense in terms of energy, that if you don't start with some type of energy, you're not going to get electrical energy. Okay, so you have to have that movement, that change in flux. Okay, we did some problems where it was like this. We did some problems where, you had, B field and time, and I gave you a graph, I don't know, whatever. Versus we did some problems where you had flux and time, and again, I gave you a graph and you explained some stuff. Okay. I think most of you seem like you're pretty good on that. Are there any questions on that you would like me to talk about? Okay. Then remember, the negative sign was its own law. Remember, the negative sign says that because remember, this is just voltage. Okay. Remember, you could use V equals IR with this, and we did. That's just voltage. Okay, Lenz's law states, hey, this voltage, if your loop is a conductor, will make a current. This current is going to have its own magnetic field. This current's magnetic field has to oppose the change in flux. And then this is where we did those questions like, hey, I have a loop, and this loop is going to move into a magnetic field. And as it moves into the magnetic field, you're going to have an increase in X's. So then if I want to oppose that, because if you look, does everybody see how the flux right now is 0? So the current is going to try and keep the flux 0. Well, in order to keep the flux 0, it needs to cancel out some of these X's. How does it do that? I mean, it's going to make some dots. So then if you grab a loop and you say, all right, well then my current, which way does the current have to go? Inside then, the current would have to go counterclockwise. Does everybody follow that okay? That makes sense?
Can we do like a couple more of those? Just like 2 more?
Sure thing. Yeah, we had, do you guys remember? Okay. We have this, so let's say we have dots here. Okay. So remember, first of all, it's only going to induce a voltage while it's entering and while it's exiting, because while it's inside the magnetic field, there's not going to be a change. So when it's entering, if we were to do those same steps, my flux is, you are here, you would be getting more dots. Is everybody with me? So if I want to oppose that change, I need to get more X's. And then that would be clockwise. Is everybody okay with the last step? Okay. And then over here, you would be losing dots. So I need to get more dots. And then that would be counterclockwise. But remember, and we talked about this, that I have kinetic energy. That kinetic energy right here is getting changed to, some of it's getting changed to electrical energy, which is why it's going to slow down. And then now it's going to stay the same, and then it would slow down again. And then eventually, where does that energy go? Well, it's caused the wire to heat up, and you'd lose energy that way. Everybody okay there?
Yeah, that makes sense.
Okay.
So the 1, 2, 3 steps, that's just to determine the direction of the current?
Yep.
Okay.
Yep. All right, and then if you remember, we also talked about that this idea that you don't even have to have a loop, okay? Like, as long as, if I have a magnetic field like this, and I have a bar, and this bar is going to move here, well, you don't even have to have a loop. If this bar is a conductor, okay, if you think about it, well, okay, the thing's moving this way, magnetic field's pointing this way. As it moves through, the top is going to end up with positive charge. Is everybody okay with Y? The bottom is going to end up with negative charge. There's a separation of charge. Separation of charge means a voltage, which is where that equation comes from. And if you look on your equation sheets, it is this last one here, right there. Okay. All right. And then last but not least, yesterday we talked about transformers and power transmission. Remember, power is I times V. So if you don't want to lose a lot of power due to heating, you need to make this small and you need to make this big. Is everybody with me? Which is going to keep the power the same because that's conservation of energy. So if you want to, when you transport power, you want to do it so that the current is small, so the wires don't get really hot. Well, how do you do that? You use a transformer, and a transformer, like we talked about yesterday, you have a coil. okay, called the primary coil. You have alternating current in the primary coil. That alternating current is going to have a changing magnetic field. If you wrap this coil around something that is iron, that changing magnetic field is going to get contained in that iron. And then if you loop something on the other side, now I have a changing flux in this coil. Well, if you have a change in flux in that coil, you're going to induce a voltage across it, and then really all I have to do is change the number of turns. So if I have more turns over here, I could step the voltage up, and then which in turn would step the current down. And then if I want to do vice versa, which you guys all have around your house, did anybody look at any of those boxes? If you look at those boxes, that you plug in, if you look at any of those things, it'll say like input 120 volts, output 9 volts. That's just a step-down transformer, okay? And then we had some really basic equations, which was, your power in equals your power out. So your current in times your voltage in equals your current out times your voltage out. And then just some ratio stuff. So the number of turns on the primary divided by the number of turns on the secondary equals the voltage on the primary or the voltage on the secondary. All right, that's pretty good timing. We're just about out of time. So, any questions? That was your last unit in